Now we're going to talk about aneurysms, tension in the walls of blood vessels, and a couple of more examples of fluid flow. So it's actually a bit of a review. Let's see. So if you look in the text, you'll see that there's a section on the elasticity of blood vessel walls, and it talks about aneurysms. And the formula that's outlined there is called T, tension. That's tension in the walls of the blood vessel is equal to delta P times R, and it's explained how that's actually similar to the surface tension formula that we've seen in spheres like air bubbles and soap bubbles, and they go through the argument. Well, the argument was I want to explain a little more carefully this thing about the similarity and differences between soap bubbles and the blood vessel walls. Okay, it's very important to understand the tension in the blood vessels because it leads to the phenomena of aneurysms. Okay, so when we first talked about bubbles, I'll draw a little bubble here with a radius r, and there's a delta P difference, meaning the pressure inside the bubble was a little larger than outside, and we said delta P, and we derived it, was equal to 2 gamma over r. And then we had pointed out, and I had explained that later on we're going to get to this, and now we are. If you had some sort of weird shaped bubble that had 2 radii, we would have said delta P is equal to gamma times 1 over R1 plus 1 over R2. Okay? And okay, I'm going to tell you already, if that tube gets really, really, really long, then what happens is that's basically what would happen if one of the radii goes to infinity, would be a tube, and that's 0, right? So we say for delta P for a tube would be equal to gamma over r. And so that is what we got from air bubbles in water and soap bubbles in air. Well, no, soap bubbles in air had an extra 2, right? Now, what happens when we're talking about blood vessels? Well, previously I had explained that soap bubbles are a little different than air bubbles. Are a little different than, let's say, something like balloons. Okay, balloons and blood vessels are different. They don't really follow the same formula. Why? Because what happens in air bubbles in water is that the surface tension is a constant. Okay, is a constant in water. Okay, so that's where you get this really weird effect that when the bubble gets smaller, the pressure seems to be larger, and so tiny little air bubbles actually have large delta P's, while a big air bubble would have a smaller delta P. And that doesn't seem very intuitively obvious because I think we're more accustomed to thinking about things like balloons, balls, things like that, where the more air you put in, the higher the pressure, and maybe the bigger it gets, right? Like in a balloon. But in soap bubbles and air bubbles in water act differently. And the reason why they act differently is because the surface tension is a constant. The reason why a bubble can keep the surface tension constant is because it actually has an infinite reservoir of more molecules to add on. Okay, so if it needed more surface tension, it can't do it. But what it does is it grabs more molecules, and more molecules come in, and the surface just gets bigger. And so the surface tension stays constant, but you just get a bigger and bigger surface. Okay, and that's what happens in bubbles. Okay, but now we're going to go and think about balloons. In the case of balloons, okay, the gamma isn't a constant, and so we rewrite it and we'd say delta P is equal to T over R, where this is going to be is going to depend on the rubber and the size of the of the balloon. I mean, before it's even filled, right? So you've got three variables actually, okay? And the only way you can explain, you can't make when we were thinking about air bubbles in water, we had only two variables and a constant. Now when we're talking about things like balloons and blood vessels, we actually have three different variables, okay? So that's an important point. And so what we do is we rearrange and we write down T is equal to delta P times R. And we realize that this is essentially like the slope, okay? So then at that point, we can start drawing a graph. I'll move on to the next thing, next page. And we could draw a nice graph like this, where we could plot tension versus radius. And this is the slope. And what that means is for example, this could be 100 millimeters of mercury. That could be your delta P. And if I had a higher pressure, we would have a different curve. And since this is the curve that describes the blood pressure in a tube, maybe we're talking about the blood pressure inside a blood vessel in your body. And what you see is that the relationship between tension and radius will take on a different line depending on the pressure. Okay? Now, the next thing is this curve. And this curve, we don't have a formula for that. That curve depends on the size and characteristics of the blood vessel. Okay, so basically, is it designed to be of a large radius or is it designed to be of a small radius, right? And here at low, the tension is going to be very low at start for low radius. And as this blood vessel gets full, okay, or the radius is forced to be bigger, there's going to be more tension on the walls. Okay, the way to think about it is like, let's say we have an empty sausage skin, and you start off filling it up just a little bit. There's going to be a tension on that sausage skin, right? And as you keep on adding more stuff into it, there's going to be more and more tension on those walls. Now, if that sausage skin was designed to be 1 centimeter in diameter, okay, fine. But maybe you could put 1 centimeter of stuff into it. But what if you tried to pack a 3 centimeter diameter of stuff in your sausage skin? It would burst, okay? It wasn't designed for that type of dimensions. That's what this curve is. So this curve here, we don't have a formula. It's going to depend on the blood vessel, okay? So that's all you have to know is that this curve looks very much like this. And then the next thing that you have to know is that, so if the person, for example, has 100 millimeters of mercury pressure in that blood vessel, and this is a healthy wall, where this point intersects, that's the radius, okay, and tension that blood vessel is going to be at. Okay? Now, what happens as someone gets older, maybe doesn't eat properly, something like that? The elasticity of the walls change. And what this says is that for the same pressure, of 100 millimeters of mercury, this new or older blood vessel wall will find itself at a larger radius, okay, and a higher tension, okay? Well, then the next thing that happens is, what happens if it gets even unhealthier than that? What happens is, this point here is a special point. This is where it bursts, okay? Remember, like in elasticity, if you squeeze something too hard or pulled something too hard, it would crack or break. It's the same thing here. That's why we introduced that stuff back then. So now what happens is you follow this red curve and you realize that it never even intersects with the blue curve, okay? The curve for the 100 millimeters. So millimeters of mercury. And so maybe had the pressure been lower, okay, it wouldn't burst. But there's no point of intersection, and so the blood vessel bursts. Now let's give you another example, okay? Let's say we have a healthy blood vessel wall and higher pressure there, okay? That's where a healthy person that for some reason has higher blood pressure, okay, would find this point of intersection. I hope you get this. And an unhealthy one would be all the way out here. It wouldn't rupture, okay, but it would find itself at a very large radius and a very large tension, okay? So this is where you realize that there are two things that can cause trouble. One is if the makeup of the blood vessel walls have lost their elasticity, even at a good blood pressure, you can cause an aneurysm. The other possibility is you have a somewhat unhealthy blood vessel wall, but your pressure has gone up too high, and it goes beyond the breaking point, okay? So two things that are bad, right? High blood pressure and compromised quality blood vessels. That's the whole section on aneurysms, okay? We move on. Okay, we're going to do an example. It's called the monstrous example. It's pretty a huge example, but it's a good one. I mean, it really catches everything. So I'll do that next.